tiempo. I'm going to go a little straightforward, so I'm going to start here. But I'm pretty sure that you already know that one of our great challenges as a society is the excessive amount of plastic waste that is generated every day and the pollution it produces. So what I'm going to introduce you today is the evaluation of using a specific solar technology for plastic recycling, and it's titled Solar Concentration Integral System with Thermal Storage for Plastic Recycling. My name, as introduced, is Ricardo Adrián Mena Pérez, and I work in collaboration with the maestro Armando Cetina Quiñones, who actually assessed me a lot in the heat transfer equations that are the most complex part of this model. The next, please. So I was planned to make a quick dynamic, but I'm gonna jump this next. Please, the next slide, next two. Maestro Rasig, por favor. Siguiente. Cambiamos, esto lo voy a saltar por el tiempo. Okay. Quickly, I've thought between two types of solar technologies for the plastic recycling. I was deciding between solar photovoltaic and the concentration solar thermal. I'm going to make a comparison with it, but what I thought it was the best, I was going to choose solar concentration thermal. So let's take with this. Siguiente, por favor. Next slide. Okay. And I think to myself that, well, we already know that commercial solar panels have an efficiency of 21 or 22%. Nos saltamos una, es la anterior, por la 4. Okay, those have between...
Disculpa, Ricardo, también tiene acceso a mi pantalla. Puedes cambiar desde tu teclado.
Okay. Gracias. Okay. So conventional solar panels has between 21 and 22%, the best of efficiency. So we start, as we see, wasting a lot of energy, and on top of that, our demand for plastic recycling requires heat, not electricity. So the transform of thermal energy from the sun to electrical and then back to thermal, actually all these transformations make the system even more waste energy and makes it inefficient. So it might be better to keep the energy the way it comes to avoid these losses using solar collectors. After all, they could start with higher efficiencies at 32%, as said in here. Okay, so then it was clear to me that I have to demonstrate that CST is better than photovoltaic for this specific application. I consider the parabolic dish collector, PDC for short, as the ideal because it can reach higher temperatures than parabolic through. Also, I was convinced that my design should implement local, inexpensive materials and to be as easy to use as possible. So I go for an all-in-one design. Of course, I didn't have the exact parameters my design should have, so it should be derived from trial and error. I mean, modeling it with numerical modeling. But what I did know were the parts of the system. Of course, the solar collector, one reflector for redirecting the sun rays, a receiver coil for the solar energy, a thermal storage tank to increase the operational time of the system, and a heat transfer fluid. Ideally, I should include a heat exchanger for the plastic extruder, but it complicated a lot the numerical model. So I limited the objective of this preliminary study as determining the feasibility of the PDC, parabolic dish collector, with thermal storage as energy supply for melting plastic. Put in other words, calculate the amount of heat the thermal storage tank can hold for 1 day and how much of it can be harnessed for the mentioned purpose, I mean, melting plastic. Okay, the model system works like this. The sun rays hits the surface of the collector, then get concentrated at the focal point where they hit the reflector that turns the rays parallel again. and then gets received by a coil in the base of the parabola. It was designed like this in order to lower the mass point of the collector so it can be moved easier than conventional designs. Okay. At the receiver, here's the receiver, the metal coil gets heated and transfers that energy to the heat transfer fluid flowing inside the coil. There's convective and radiative losses, and the remaining energy is carried all the way to the storage tank. Now here we see the storage tank, and at its entrance, the flow is divided in various tubes that cross it vertically and slowly heats the thermal storage material, TSM. Then the fluid gets out of the tank with a lower temperature, but still higher than when it started. So it enters in a positive feedback loop until the tank reaches the minimal operational temperature and heat gets extracted for the intended purpose. Basically, this is the way the numerical model works. Now, many design considerations were taken at every stage that affects the behavior and the amount of the heat that is transferred in each step. So let's start with the collector. A 2.3 meter diameter plate was proposed for easy manipulation, covered with mylar instead of mirror or aluminum for minimizing the weight, as the metal, normally this metal weighs much more, but still has similar reflectance. Then go to the reflector. It's made with telescope grade mirror of 98% reflectance, and because it's as small as 8 centimeters of diameter. The receiver is made of 1 millimeter wall thickness copper coil, 4 millimeter diameter with black paint coating. It's designed as planar because the rays it receives are parallel, and there were modeled 2 different heat transfer fluids that are both parameter dependence of temperature. So it was evaluated with this both. But the most important part of the system was the thermal storage tank. With a shell and tube design, its dimensions were variated as well as the amount of tubes inside until reaching the desired temperature. 4 configurations were modeled, considering 1, 7, 19, and 55 tubes. The importance of these configurations is to achieve the smoothest thermal distribution with a minimum amount of tubes. The image, the video shown here is quite enlarged, so it's actually it's circular, but anyways, it's the result of a simulation. Then, moreover, the materials selected as thermal storage materials were derived from a previous work in which different coupled heat transfer fluid with thermal storage material were simulated to study the charging time and the energy stored. From its results, gravel and thermal oil were selected to build the storage tank here. So, in order to increase the heat transfer, the gravel was saturated with the heat transfer fluid, and the equations for modeling this kind of mixture is shown as here. Now, the system as a whole were modeled in MATLAB using a stationary regimes that vary in each timestamp with a 1-year database of 10-minute frequency. And in essence, what the model does is the next. Both the heat transfer fluid and at the receiver and the thermal storage material starts at room temperature as shown in the graphic. But as soon as the sun starts getting harvested, temperature of the oil rises and it moves towards the tank. In consequence, the thermal storage material follows accordingly, but with a lower temperature. Our goal is to reach the melting temperature of plastic HDPE, which is at 209 centigrades, plus a slight threshold. And once it reaches that point, a constant amount of heat is taken, simulating the demand for plastic melting. As you can see, the heat flux of the thermal storage material, TSM, is reduced drastically and its temperature maintains constant for a while. Then the influence of the sun getting down makes necessary the use of the stored heat in order to maintain production. It continues this way until the temperature of the thermal storage material becomes lower than required. Then the process stops completely, and the only heat fluxes remaining are the losses by convection and radiation. Here, insulation at the tank is critical to avoid massive losses during the night, because in fact, it takes up to 3 to 5 the average days to reach this stability point. It's not that fast, but after reaching that, calculations can be done. And data use was averaged in 12 representative month days to calculate the yield of the whole year. And by doing this, the system achieves a total 3.13 megawatt a year energy production. Put it as an indicator, it results in 754.3 kilowatt hour a year by square meter. If we compare it against photovoltaic, it will produce 384.9 kilowatt hour a year by square meter. It's roughly half of the energy in the same area and under the same conditions. But definitely here solar panels are much cheaper by various factors, and we don't even have to make math. But by comparing both in different aspects, CST has a denser energy production, thus requires less space, as we just see. But definitely, photovoltaic requires less maintenance since it doesn't have moving parts. Also, structure is more secure against high wind bursts. Photovoltaic is much easier to install. The market and the production of photovoltaic is much more developed than the CST. Both have available materials for production, but most importantly, photovoltaic is much cheaper than CST, which in turn, it can ensure a faster investment return. Okay, and as a conclusion, concentrating solar thermal is less competitive than photovoltaic for this specific application in plastic melting and recycling. This one, the photovoltaic, has a much more developed market and established supply chain. It is mature technology with modular equipment that allows it to adapt to almost any demand with the addition of batteries. It has a great advantage against the majority of renewables to be easy to mount and install with very low prices that keeps falling every year. Now, CST technology, as presented in this work specifically, only can be an option as a project if the surface occupied is the most important, the most relevant factor. Now, and finally, it might seem like photovoltaic is getting so much popular, so much attention, that maybe the supply chain cannot support this growth. But there have been studies from these two authors presented in the slide demonstrating that even with a total transition to solar 100%, the supply chain can accomplish the task, being 100% renewable and solar, without exceeding the actual growth that it has today. Just glass has increased its production, but everything else, including silicon, is just okay. There's a space to consider a different type of concentration solar with a Stirling motor that can be even more, even better than CST, and maybe compete with photovoltaic. But that were my conclusions for this quick study. Thank you for your attention. Y al final las preguntas las pueden hacer, son las referencias y las preguntas las pueden hacer en español si es que hay.
Ok, muchas gracias, Ricardo. La verdad es un tema muy interesante y muy innovador en el aspecto de pues el reciclaje de cualquier empresa de reciclaje. Bueno, pues el uso de la energía que utilizan para ahora sí para hacer el reciclaje, pues debe ser en teoría menor a la que sacar el material desde su principio de vida. Pero bueno, por el tiempo